Today, I'm going to introduce you to a quantum computer that can be unfamiliar to you. I'm gonna talk about how quantum computers work and how they change. Quantum computing has become one of the representative applications of quantum physics. Quantum computers have the ability to solve problems that require very complex calculation at a rapid pace. Now, let's see how quantum computers are handled. Classic computers encode information bit by bit, and each bit can represent a 0 or 1. These zeros and ones act as on-off switches that translate into calculation functions that perform simple calculations. Just as classic computers have bit, quantum computers have qubit. This qubit uses two key principles of quantum physics: superpositions and entanglement. Using superpositions, 0 and 1 can be obtained probabilistically at the same time. This means that each qubit can represent both 0 or 1 at the same time. In addition, quantum entanglement is also used. If a particle and a particle are physically related, the moment the state of one particle is determined, the state of the other particle is also affected and the state is determined. Using these two principles, qubit can act as far more sophisticated switches, solving difficult problems that quantum computers are virtually impossible with conventional computers. These features make quantum computers even more powerful. For a classic computers, when n represents the number of bits, it can display and check only one system state at a time. However, an n-qubit computers can obtain a result of 2 to the nth power in parallel when the number of qubits increases to n. This means that every time you added one more qubit to a quantum computer, you double the number of states that can be displayed and inspected. When the power increases exponentially with the entanglement of qubits, quantum computers can solve certain problems much more efficiently. Let us sum a 3-bit binary data stream. If there are only 2 possible states, you can understand that 8 results are possible because there are 3 bits to raise to n. Therefore, 8 possible outcomes and all probabilities must equal 1 here. Also, the probability that the 3-bit binary systems will yield one of these values is 100%, because it is the only possible value in 3 digits and 2 numbers. However, the quantum 3-bit system works slightly different. Because each qubit can represent any complex number of between 0 and 1, the sum of square for each of the multiple probabilities must equal 1 for the 100% probability. When we make a measurement of a 3-bit quantum systems, the value of the particles in each orientation collapses to a classic state of binary. By the computational power of a 3-bit quantum computers far exceeds that of classic systems where binary systems require to raise to the power. Two more explain the difference between these two computers in a maze-solving method. A classic computer solves a maze-like problem by testing each possible path one at a time. However, quantum computers use entangled quantum states to find the correct path faster with much less computations. In this way, quantum computers have the potential to provide solutions where patterns are invisible. This is because there is not enough data, or the likelihood of finding an optimal answer is too great to be processed by a classic computers. In other words, quantum computers will show excellent performance in the case of molecular simulations or path optimizations where successful results must be obtained by making multiple attempts at a time. rather than a problem of producing one operation results at a time. Maybe it can help the financial service industry make better investments by modeling financial data and finding new ways to isolate key global risk factors. However, quantum computers still have many problems to solve. If this is solved, quantum computers will be able to help our lives in even more amazing ways. Thank you for watching the video so far.